Okay, let's dive right into this explainer. Today, we're embarking on a highly visual journey into the invisible atomic structures that give metals their incredible strength. You know, we interact with steel, aluminum, and copper literally every single day, but we rarely stop to think about why a steel beam can hold up an entire skyscraper, while an aluminum can just crushes under a simple squeeze of your hand. So using Professor Akhtar's fantastic engineering materials lab framework, we're going to visually dissect exactly how hardness and heat treatment actually work. Here's our visual blueprint for today. We'll cover the scale of hardness, the heat treatment journey, peek inside the microstructure, learn how we measure the invisible, and finally, look at real-world applications. All right, part one, the scale of hardness. Let's see how these materials actually stack up against each other right out of the gate. Now, when we map out the vast ranges of hardness across different materials, it's pretty fascinating. Engineers quantify this strength using three main scales: Brinell, Rockwell, and Vickers. So picture a material like aluminum. It sits incredibly low on the scale, with a Brinell hardness of just 25 to 40. Copper is right in that same neighborhood at 35 to 60. But as we move past things like brass, bronze, and cast iron, those numbers really start to climb. Once we hit tools steel, we're looking at Brinell numbers between 250 and 350. And then, at the absolute peak of our scale, hardened steel. It totally tops the charts, ranging from 350 all the way up to a massive 650. Visually, the leap here is just dramatic. When you put hardened steel next to basic aluminum and mild steel, it completely towers over them. I mean, mild steel is a great everyday workhorse, coming in around 140 on the Brinell scale. But hardened steel, sitting way up there at an average of 500, that gives you a crystal clear picture of just how vast the spectrum of material strength really is. But that brings us to the multi-million-dollar engineering question: how exactly does steel get to that towering height? Well, the crucial thing to understand is that a metal's strength isn't just about what it's made of. Sure, chemical composition matters, absolutely, but hardness is essentially a three-part puzzle. It depends on that chemical composition, yes, but also the heat treatment and the resulting microstructure. You could literally take the exact same piece of carbon steel, and just by changing how you treat it with heat, you can make it soft enough to bend in your bare hands or hard enough to snap under pressure. Which brings us to part two, the heat treatment journey. Let's look at these thermal shocks. To truly understand how we manipulate that internal structure, we need to explore this intense, fiery process. Heat treatment is basically a sequence of very precise thermal shocks. First up is annealing. This is where you heat the metal, hold it at a specific temperature, and then let it cool incredibly slowly, usually right inside the furnace. Visually, think of this as relaxing the metal. It softens it, removes internal stress, and makes it way easier to machine. Next, we have normalizing. You heat it up again, but this time you pull it out and let it cool in the open air. This refines the grains, making them highly uniform. Then comes hardening. You heat it back up, but instead of air cooling, you plunge it rapidly into water or oil. This sudden, violent shock freezes the atomic structure in a state of high tension, massively increasing its hardness. And finally, tempering. You take that intensely hardened metal, reheat it just a bit to a lower temperature, and let it cool in the air. And that final tempering step, it is absolutely vital. If you picture a fully hardened piece of steel right after that rapid cooling, yes, it's incredibly hard, but it's also brittle, almost like glass. If you strike it, it might just shatter. Tempering takes that brittle, highly stressed internal structure and gently relaxes it into something tough and usable. You're sacrificing just a tiny fraction of its hardness to gain a massive, massive amount of toughness. Section 3. Inside the microstructure. Time to look at the atomic ships. Let's zoom way in and look at what is physically happening to the metal on a microscopic level during all this. How do engineers even know what temperatures to use? Well, they use the iron-carbon phase diagram. Think of this as an engineer's ultimate treasure map. It charts exact carbon percentages, from 0 up to 2%, against temperatures rising all the way to a blistering 1600 degrees Celsius. Those steep, jagged curves on the map, they show precisely where the metal shifts its internal grain structure, from ferrite to austenite to cementite. When you cross those critical temperature lines at 727 or 1147 degrees Celsius, you are literally forcing the iron and carbon atoms to completely rearrange themselves. And depending on exactly where we land on that map and how fast we cool the metal, the microstructure visually and physically transforms. When viewed under a microscope, these structures show this beautifully. An annealed structure looks almost bubbly and relaxed, which is why it's so soft and ductile. The normalized structure is beautifully fine-grained and tightly packed. The hardened structure
It looks like jagged, microscopic needles, perfectly explaining why it's hard but brittle. And that tempered structure looks like a beautifully blended, highly cohesive matrix. It's wild, right? Completely different mechanical properties for the exact same piece of steel. But how do we actually prove that our heat treatment worked? We obviously can't see the atoms with our naked eyes.
That brings us to Section 4, Measuring the Invisible. The answer is surprisingly simple. We physically dent the metal. This brings us back to those hardness scales we talked about earlier. First, the Brinell hardness test. This one is designed for softer materials, castings and forgings. Visually, just imagine taking a highly polished, heavy steel or tungsten carbide ball, which is represented by a capital D in our formula, and driving it into the surface of the metal under a heavy load, represented by P. We then measure the exact diameter of the circular crater it leaves behind, the lowercase d. We plug those visual measurements right into the formula, and boom, we get our Brinell hardness number. Now, for a broader range of metals, including the much harder ones, we switch to the Rockwell hardness test. Instead of a large ball, Rockwell uses either a really sharp diamond cone or a smaller steel ball. But the crucial difference here is how we measure it. While Brinell measures the width of the dent, Rockwell actually measures the exact depth of the indentation, represented by the letter H. Basically, the deeper the penetrator goes under a specific load, the softer the material is. And finally, we have the Vickers hardness test. We use this for very thin or extremely hard materials where a heavy ball might completely ruin the sample. For this one, picture a microscopic, flawless diamond shaped like a pyramid with exactly a 136-degree angle at its peak. The machine presses this diamond into the metal, leaving a highly measurable, perfect square dent. By looking through a microscope and measuring the average length of the diagonals of that square, our lowercase d, we can calculate the Vickers hardness. It is an incredibly precise visual measurement. Section 5, Real-World Applications. Let's talk about engineering the future. So, why do we go through all this trouble with fiery furnaces and diamond indenters? Because mastering these invisible microstructures is literally what unlocks the modern world. Understanding hardness testing and heat treatment dictates the exact selection of materials for any mechanical design. Engineers use these precise processes to purposely improve strength, hardness, and wear resistance exactly where they are needed most. I mean, this is how we build high-stress engine components for cars and aerospace vehicles. It's how we create tools that can actually cut through other metals, and machinery that doesn't just break down under constant friction. Ultimately, this exact science drastically enhances the service life and performance of virtually every structural component around us. But of course, manipulating heavy metals at extreme temperatures and crushing them with diamond indenters is, well, dangerous work. That's why Professor Ochter's lab guidelines are incredibly strict. Whenever you're dealing with these materials, laboratory safety is mandatory. We're talking safety goggles to protect from flying debris, heavy gloves to handle scorching metals, lab coats while avoiding any loose clothing, keeping your hands completely clear of the moving parts on those heavy testing machines, maintaining a spotless workspace, and instantly reporting any accidents. Safety is just as vital as the engineering itself, for sure. It really does make you appreciate the engineered world around us, doesn't it? Behind the smooth, polished surface of every steel tool, every car frame, and every airplane wing, there is a complex, microscopic architecture that was deliberately shaped by fire, force, and extreme cooling. I really hope this explainer has sparked your curiosity to learn a bit more about the materials shaping our future, and to look at the metal objects in your everyday life, not just as solid blocks, but as brilliant, microscopic tapestries of science.